Next speaker, the Dr. Katharina Senkalla, who is a postdoctoral researcher at the University of ULM, Germany, where she's also completed his PhD degree. Her research focuses on quantum network based on group colors centered in diamonds, exploring the coherence of spike control, optical interfaces, and nuclear spin memories as building blocks for scale quantum communications. She has been involved in several collaborative research projects advancing solid-state quantum technologies. It's a pleasure having you here, Dr. Katharina Senkalla. You can go ahead with your presentation.
Oh, thanks for the very nice introduction. And I'm super happy to be here to be part of this very great event. And yeah, so as already said, so I'm a postdoctoral researcher, so a little bit maybe a bit of contrast what you have already heard from the industries talk before. Um, and I'm from the Institute of Quantum Optics and University Ulm. And maybe the first question you could ask yourself is, and quantum. What does it has to do with each other? So maybe you even wonder where is even Ulm? And here you can actually see a map of Central Europe, and Ulm is actually located in Germany, which is actually more or less in the center of Europe. And here in particular, we are located at the southwest of Germany, which is not too far apart from Munich, which you may know from the Oktoberfest with pretzels and some beer. So you could also maybe know Germany and in particular Ulm because of its church, the Ulmer Minster, as with the 161.53 meters, this is almost the highest church tower of the world. Why do I say almost? It is because just a few weeks ago, La Sagrada Familia in Barcelona was catching up and is now about 10 meters higher. So, but let's move back to what was really from interest here. And this is, what does Ulm have to do with quantum? And first of all, Ulm was the birthplace of Albert Einstein, which was one of the most important persons of the foundation for quantum mechanics with his discovery of the photoelectrical effect about 100 years ago. Moreover, Ulm is actually supporting quantum education quite well. So just 1 year back, we established a new master's study, which is the quantum engineering studies. Also, Ulm has a very lively quantum research. So it is within the different institutes of the university, as well as in some centers, which are actually connecting the quantum research across south of Germany, as well as in some federal funded projects. And also, very recently, actually, the German Aerospace Center decided to build one of the central stations in Ulm, going for quantum technologies and having some big quantum computing initiative. In all of this, we have a lot of quantum startups spinning out of this Ulm's quantum ecosystem, as ranging from the quantum sensing part over to the quantum computing part in so many different ways. But of course, if we have a look on actually the bigger scale, so the world's quantum ecosystem, we are just a small part of it, which I try to sketch here with showing a lot of different companies working in the quantum field on different platforms even. There's one thing which all of these companies have in common, and this is one central question, is how to scale up. And here is like, I don't want to say that, I want to say that actually all of these platforms, they were made some great advances. However, there are still a lot of single isolated quantum devices. And if you want to think about a real scalability, we need to think how to go beyond a single quantum device. How can we connect into something bigger? And this is actually where the vision of a worldwide quantum network is emerging, which is the idea to link different quantum devices across the whole globe and allowing then to do some nice things as quantum communication, distributed quantum computing, quantum enhanced sensing, or applications we even don't know yet. It is a way to overcome the limitations of size and complexity of single quantum devices by sharing entanglement of distant quantum device partners. With that, I want to come to the outline of my talk, which is kind of like I want to first kind of like introduce from the vision to the building blocks. How does actually the entanglement distribution works? How can do the quantum repeaters come in there? What defines a good quantum network node? Why diamond? And then having a look on the Germanium Vacancy Center as a particular platform as a quantum network node, and concluding and giving you an outlook on this topic. So let's start. So with the question, how can we connect now very distant quantum devices with each other? As usual, let's just call them Alice and Bob. And now the question is, how can we reach these different distances? And one of the major building blocks is actually this section here, where we have a quantum memory, which is emitting a photon. And in the middle, we observe some entanglement swap. When you have a closer look on this, you can see it here. What happens is we have first the quantum memory entangled with the photon on both sides. This photon is then thrown onto a beam splitter and measured then simultaneously on a detector. By measuring the photons on the detector, so performing a bulk state measurement, we can perform an entanglement swap, so swapping the entanglement from the memory and the photon to the photon and the photon and the memory and the memory. And with that, building a fundamental entanglement link. This distance of the two memories is here clearly defined actually by the coherence time of the quantum memory. As if it's loose coherence time, we cannot really generate entanglement anymore. And the other part is actually the losses of the photons, which can happen within the channel. But when we now have several of these building blocks, we can just put them one by one after each other, and by that kind of like part by part enhancing the distance. Now there's another very important crucial step, which is actually that we need to bring Alice and Bob together. So it's nice to have that we have the different entanglement segments, but we now need to connect them with each other. And this is actually done by performing another bulk state measurement on the quantum memories. And how does this look like? So I don't want to go too much into the detail here, but actually what we do is that we are doing some local operations consisting out of a CNOT and a Hadamard gate, and doing some simultaneous measurement of our quantum memories. By then doing so, we're doing another entanglement swap. In this picture here, entangling the two inner quantum memories with each other, and by having the entanglement swapping mechanism, this also now entangles the two outer quantum memories. So now that we know how we can build up this distant entanglement, we would like to know what are actually the requirements for a single quantum network node. And I mean, like I have now shown you the different steps here very closely, of course, but to make something very clear, which is what we need. So for the first step, actually, we definitely need actually an efficient line matter interface, and also a very long memory time to establish a viable entanglement segment in the first place. Additionally, we want to have a multi-qubit entanglement. Why is that the case? This is the case because this enables us actually to do this operation, which is shown here in the middle line. So what I told you as the second part, so doing an entanglement swap on the quantum memories, as well as to cope for errors which could occur. For example, even like due to the losses of the photons, or due to um, some um, yeah infidelities which we observe within our gates. So with that, now knowing what we need for a quantum node to be efficient to work out, and connecting Alice and Bob over large distances, I already want to move on to the next question, which is, why should we use diamond? And now, again, look on what we have just figured out for the quantum node. So we want to have some efficient light matter interface of photons interacting with a quantum memory, want to have a quantum memory interacting with a quantum register. And if we now a little bit translate what we have here as requirements into the solid state platform, which the diamond indeed is, we can actually reformulate it that we need some photons which are interacting with some electron spin, and some the electron spin which is interacting with the nuclear spin. So now, why diamond? Diamond has a lot of great properties, which you probably know, which is, for example, its hardness. That's the hardest material on Earth. It is a very chemical inert. But for the question we want to tackle here in the sense of the quantum node, it is actually that we have an optically accessible individual controllable spins, the so-called color centers, and we have quite a zoo of color centers within Diamond. Um, as well as we have a lattice which provides a long-living nuclear spins, which can then be used for the quantum register to make this fault-tolerant quantum communication or also quantum computing. Another very nice effect of the diamond is that we can fabricate some nanophotonic devices out of it, so we can get some on-chip scalable quantum repeaters, quantum nodes out of our diamond. So with that, I want now to shift a little bit the gears to kind of like having a very close look on the different requirements which we now set for the quantum node, speaking the efficient light matter interface, long memory times, and multi-qubit entanglement. So let me start with the efficient light matter interface. And in particular, when we're talking about an efficient light matter interfaces in diamond, we are thinking about a certain family of color centers, which is called the group 4 color centers. I tried to make here a small illustration how this could look like. We do have actually our diamond lattice. We remove 2 of the carbon size within the lattice and introduce a foreign atom, which is actually out of the group 4 family, which could be, for example, the silicon, the germanium, the tin, and the lead vacancy center. All of them forming this structure. Why is this so interesting? And coming back to the part of the efficient light matter interface, it becomes evident when we have a look on their spectrum. And you can see that we actually have a bright coherent single photon emission, means that we have a high amount of the overall fluorescence located within the so-called zero phonon line. This ensures that we do not have any phonons interacting with them, so speaking that they are coherent with each other. Additionally, what you might have noticed is that we have with this structure as an inversion symmetric structure. This makes actually the optical transitions insensitive to electric field perturbations of the first order, which is very important for the entanglement scheme of the entanglement segments. So furthermore, when we look now also what we can do, and what I already mentioned is that we can now take our diamond and incorporate it into nanophotonic structures, even either kind of like having a nano diamond, just putting on some structure, or it is also possible to fabricate a full nanophotonic cavity, for example, out of the diamond. So for now, I have introduced the full family of the group 4 color centers. However, for the next rest of my talk, I want to actually focus on the germanium vacancy center. So with that now said, let's move on. So to the spin photon entanglement principle. So I've just already shown you how this could work, that we have our two quantum memories, which are first entangled with the photon and later then entangled with each other. How does this look actually like when we have a solid state qubit? Here you can actually see the scheme, how this works. So we have some qubit system, in particular here with up and down. We have some excited states. And we can, in our case, optically initialize our spin. Then we go into some superposition. We scatter a photon up on it. Depending on the spin state, it will emit a photon or not. So if we would be in up, it would emit a photon. If we would have been in down, it would not. If we now put some pi pulse in between and repeat the whole sequence, we should actually, even if we have not emitted a photon, get now a photon. And with that, actually, we are finishing the scheme, and we will have for sure some entanglement of our of the emission of our photon with the spin state. So how now do we realize that with our germanium vacancy, which we have in diamond? So first of all, we need to have some qubit state system, and to kind of like trying to sketch it here. So here you can see some reduced energy level scheme, which consists of some ground state and excited state, which are splitted by some spin orbit coupling. And to now get to our qubit manifold, we have to first apply a magnetic field, which is in our case about 100 millitesla and aligned along the germanium vacancy principal axis. So for now, this optical initialization and scattering, we now use some resonant laser, which is either on the transition C1 and C2, and depending on which transitions we are using, we can polarize into the other spin state, as also sketched here in the first part of the entanglement principle. To do the coherent control, we can simply actually apply some microwave driving field, which should then shuffle our up and down spin with each other. And by doing so, we can, for the initialization and readout, we can achieve fidelities of 98.7%, and for the coherent control, something like 6.486 megahertz. So with that on hand, I want to tell you a little bit more how efficient is actually efficient. And this is actually depending on one property, which is called cyclicity. Cyclicity means how many times can I actually scatter a photon before I observe a spin flip. And it's not hard to see out of the scheme, which you can see here in the top right corner, that this is actually depending on the upper state here. So kind of like the transition probability to go into the other spin state. And we can actually control this by adjusting our magnetic field orientation towards our principal axis. So the closer we come to the principal axis, the less probable it becomes that we will observe a spin flip. Now, that is something we have done, and actually we could achieve a cyclicity of about 10,000. That means we can scatter 10,000 times a photon to our group 4 color centers before we observe a spin flip. What this actually means is when we now record, when we now scatter a photon, have we observed a photon or didn't we observe a photon? So speaking, if we're now looking on this histogram, so the green one here is actually the dark histogram. So I have scattered a photon and I didn't get any photons back. And the blue one is actually when I was in the bright state. So when I have scattered a photon and got a photon back. And you can see clearly that we have some distinct distributions, which allows us to do some single shot readout. So basically, when we shoot one photon, so we only need one photon to decide whether we are actually in a dark state or in the bright state. This value is actually currently record for the germanium vacancy center in diamond. Okay, great. So we have a very efficient spin photon interface, but what is about the quantum memory property? So let's look back on the energy level scheme, and there's something which I have not introduced to you so far, which are these wavy lines. These wavy lines are actually um, phonons, which are coupling to the different energy levels. And you can see actually that our qubit is suffering from some phononic dephasing. What does that mean? When we now kind of like make a zoom in into the slower energy level scheme, we can see it here again. We can see that we have the two manifolds, and in particular, the evolution of our qubit system is different within these two qubit manifolds. Um, as the nature of the phonons are a stochastic one, it's not easy kind of like to cope for this effect, but there's a kind of like very simple solution, which is actually freeze out the phonons, get rid of them, such that our coherence time, our memory time is not affected yet. When we now look on our germanium vacancy center, that means we need just to decrease the temperature. And when we're carefully calculating how much we have to decrease the temperature, this is actually depending here on this ground state splitting denoted by delta G. We can see that we have to operate below a critical temperature of 493 millikelvin. So that means actually kind of like in simple terms, we just need to take our system and brute force, blue force it to be at lower temperatures than 493 millikelvin. So speaking, we need to work in a dilution refrigerator system. When we do so, actually, we could observe that we can get rid of all the phonons which are harming our qubit system, and we can get coherence times using a Hahn-Lecker sequence already of 440 microseconds, which is quite nice. However, this is not the ultimate limit yet, because we are now encountering a new challenge, which is the qubit environment. So how does now affect us? So let's have a look back. Okay, how is our coherence time affected for group 4 color center? The first limit which we face is the phonon limit, which we just overcome by putting it into the blue force system. The next thing we are encountering is actually the limitations of the environment, also sometimes called the spin noise limit. There's actually a technique which is called dynamical decoupling, DD, which can help to overcome decoupling to the environment. How to do so? So this is actually by doing some control pulses, usually pi pulses, with a certain phase and a certain time distance to each other, which then should decouple from the environment. Does this already is enough to actually reach the performance of a quantum memory? Not quite. So what we have to consider is that all of these control pulses, as these are microwave pulses, are introducing heating into our system. If we have too much of the heat load, we are raising our temperature, and it can be that we eventually are not below the critical temperature anymore and are back to our phonon limit, which is in a few nanoseconds regime. So what do we need to do to actually get rid of this, or to tackle this challenge? So there are several things we can do, and one, of course, a very simple one is actually to reduce the duty cycle of our pi pulses compared to the waiting times in between, to lower the heat load, but still allow for some efficient decoupling. We simulated here quite a lot. So which tau can we use and find some balanced solution, which allowed us to prolong our memory times from the 440 microseconds up to the record value for group 4 color centers of 20 milliseconds. This value is higher than almost 2 times higher than what was reported for the other group 4 color centers so far. So it's really nice to have a system with this record T2 time. But is this now then already quantum memory? And here we can now say, yes, this is a quantum memory. We can actually preserve our coherence time using our dynamical decoupling sequences, and we can preserve it for 20 milliseconds. So with that, I want to already come to the question of how to do the multi-qubit control. So we have heard that we want to have some fault-tolerant quantum computation or a fault-tolerant quantum communication. And for this, it is just necessary to actually individually address several nuclear spins within our system to perform the different protocols necessary for fault tolerance. That means we have our germanium vacancy center, and out of the C13 path, which is actually natural abundant within our diamond lattice. So because I'm not so sure how familiar you are with that, in our system, usually in a diamond, usually you have C12 carbon atoms, but there are about 1.1% of so-called C13 carbon atoms, so it's a different isotope, which carries a spin of 1/2. This is in contrast to the C12, which doesn't carry any spin. So we want to now address the different C13s within our spin bath. And I just told you, okay, the environment is bad. So we don't want to actually couple to the environment because this is actually harming our coherence time, our memory time. But we can also use dynamical decoupling to enhance the coupling. So to find some, in this case, some tau spacing, which is actually just resonant to one of these different C13 spins in our path. So, however, there's a little bit a tricky part here using group 4 coalescenders, which is that when you have a careful look here, let's just guide you through here, is that the resonance is depending on some order. So P is just some order. Omega 0 and omega 1 are just kind of like the different lambda frequencies depending on electron spin states. And when we make a careful calculation, we can actually see how this is depending actually on the spin states. So S0 and S1. And for spin 1/2 system, the thing is that this term is actually canceling out. S0 is -1 and S1 is equal 1/2. So we have 1/2 minus 1/2 gives 0. So we're completely not sensitive to this term anymore. And when we're having a careful look here, we are only second order sensitive to the hyperfine coupling parameters, so it's to the coupling parameters of our different C13 spins. This poses actually a great challenge for group 4 coalescenders when we're really talking about establishing a real quantum network now. And we now found some technique which allows us, despite this kind of like insensitivity, to selectively figure out where is our C13 and how can we address it. And this is what you can see here. Please don't be afraid. I will guide you through this pulse sequence here. So we have, again, some lasers, some optical initialization of our spin system. We are going into some equatorial plane where we are performing some dynamical decoupling sequence and having some conditional rotation of our electron spin depending on the state of the nuclear spin state. We repeat all of this after a correlation time tau, which has to be longer than the dephasing time of the electron spin to avoid unnecessary harmonics in our signal. And then just again repeat the full block with the dynamical decoupling sequence. And in the end, we just measure out. What happens is we have some conditional rotation of our electron spin in the first block of our sequence, which we correlate to a conditional rotation in the second half. And this conditional rotation is always depending on our nuclear spin. And the nuclear spin, in particular, we're currently sensitive to which we are coupling to. So when we now do a scan of the tau d, so first of all of the tau, and then also of the tau dd. So um, let me tell you this. So if we are having a certain tau dd, we can be very sensitive to single nuclear spins. Having this correlation time tau, which we are actually varying, so we have here an array which we are varying, we can actually get some oscillations depending on our nuclear spin, which should show directly the two lambda frequencies in which actually the nuclear spin can process depending on the electron spin state. If we now plot this as a two-dimensional plot, as here, you can see here's the effective lambda frequency. So basically, the frequency my C13 is rotating or processing around depending on my electron spin state. And the interpulse spacing tau dd. So I'm actually changing my sensitivity from the one to the other nuclear spin. And you can actually quite clearly see that we have here, for example, this part where we have, for example, here more strongly coupled C13 present, which is actually yielding us the two frequency of about 500 kilohertz and 2500 kilohertz. When we're now looking on a little bit different position, which is here, we can actually see that we have another nuclear spin, which is more weakly coupled, but it also shows the two different lambda frequencies depending on the electron spin state of our group 4 color centers. So this shows that this technique is actually really allowing us to identify several nuclear spins within a full spin path, and which is very crucial then for building our multi-qubit registers. So the next step is, I guess, quite obvious. So we don't want only to identify, but we want also actually to control our C13 spins. So, and let's start for that with our the coherent control of our more strongly coupled C13. So here we can actually use quite easy schemes to initialize it using some swap gate with some selective control pulses on the different energy levels. We can use some direct RF driving, where actually the lambda frequencies which we have determined before can be directly used. For example, here we could achieve then a Rabi frequency, so a frequency on which we can flip our qubit of 11.73 kilohertz, which is quite high actually for nuclear spin systems of coupled to group 4 color centers. So now having here some coherent control by hand, we can again go one step further and try to map our coherence times by just, again, also decoupling from the environment. And that's something you can see here. So for a single pi pulse in the middle, so for kind of like almost no decoupling, we can actually have already something about 300 milliseconds. By increasing the number of pulses, we can actually push the boundaries further and further and further until we reach here for 16 pulses in the CPMG sequence, as it's called. We can already achieve memory time of 2.57 seconds. So this is actually also record coherence time using group 4 color centers and addressing C13 spins. But this is not enough. So this was actually like what we measured, but then we tried to estimate, okay, how much can we push it further? And this is what you can see here in the small inset. So we were plotting kind of like the interpulse spacing, so the spacing between the different pulses, and we mark here the region, the gray shaded region is marking actually pulse spacings which are not possible in our system due to the heating which takes place. And you can see also the boundary from given by the electron spin lifetime. And by choosing interpulse spacing of about 20 milliseconds, we could even push actually the memory time up to 18 seconds. So this is very nice. This was from the one spin, but we also, of course, want to see it from the other spin. And here we have actually followed a different approach. So on the left-hand side, you can see some direct driving, some direct control using RF, like radio frequency driving fields. And on the right-hand side, we have followed a little bit different approach, which is the so-called indirect driving. What do we do? So we use actually the electron spin and kind of like push it in a certain way back and forth to make the nuclear spin slowly spiral down and actually fulfill also Rabi oscillations, which you could see here. Um, with that, we were also then able to perform at least here some measurement of the dephasing time. So speaking, no decoupling pulses yet. And we could achieve already something about 1.5 milliseconds or yeah, so around 2 milliseconds actually even only with dephasing time. And it is considered that we can push it even further. So now, with that, I already want to come to my conclusion and outlook to give you enough time to ask me questions a lot. So let's have a look. We have the setting of a germanium vacancy center within our diamond, and we want to fulfill all the requirements of a quantum node. So we want to have an efficient light matter interface, we want to have the long memory times, and we want to have some multi-qubit entanglement. So let's look back what I've shown you. Regarding the efficient light matter interface, I have shown you that by tweaking actually our magnetic field and achieving very high cyclicity, we could enable some single shot readout measurements, which is actually quite a proof that we have some efficient light matter interface. The second thing I wanted to show you is that we have very long memory times. And for that, I showed you actually that we need to overcome the photonic dephasing. We needed to overcome the coupling to our environment. And by choosing some balanced value of the tau spacing within our control pulses, we could achieve a memory time of 20 milliseconds, which is up to date record memory times for group 4 color centers. And last but not least, so I showed you that we can actually selectively address at least, so we can identify 3 of our spins and we can selectively address already 2 C13 spins out of our spin path, which demonstrates our multi-qubit control. However, when we're looking on the requirement of the multi-qubit entanglement, it's only half fulfilled, so we have to go one step further and we have to prove the real entanglement between the different C13s and also the electron spins. So when we now go to the outlook, it's quite obvious what has to happen next, which is actually transforming the multi-qubit control into some multi-qubit entanglement. However, I want to emphasize that now I've shown you already something with the germanium vacancy center, but there's a lot more progress going on. For example, on the platform of the silicon vacancy center, the vision already started to become reality. So the vision of a quantum network based on color centers in diamond was shown to become reality. What they have shown and what they have done great work is actually they have already incorporated their color centers within nanophotonic cavities, used some frequency conversion, and could demonstrate some entanglement of the quantum memories in a telecom network over quite some distance, which was about 35 kilometers in a metropolitan network. However, so they were restricted to only one additional nuclear spin. So this is something where we can think we can enhance this work and with our technique to selectively address the C13s, put some other effort. Also on this system was shown that it's possible to do some universal distributed blind quantum computing. So what I've just told you at the very beginning, quantum network allows you to do some great stuff, which one of them is actually distributed quantum computing. Another one is blind quantum computing. And this means actually that the server is completely blind what the client is doing. So you can do what is already maybe now known, some cloud computing, but on a quantum basis without giving the possibility to the server to eavesdrop yourself. Again, so this was great work done and absolute great achievements. And we think that we can, with our system, where we are now able to actually address several multiple C13 spins to allow even for more fault-tolerant processing algorithms and also push their boundaries further. And also to tell you another example, just very recently, there was also the paper coming out about the non-optical interferometry in a quantum network. So not only quantum computing is possible, but also enhanced quantum sensing. And this was all already shown on the platform of Group 4 color centers in Diamond. And also that this is not just simple research. I don't want to make here some advertisement, but I know that for the work which was now done with the silicon vacancy is now pushed forward from the company INQ, which was actually acquiring the initial company LightSync, and with that, kind of like building some commercial ground base to push all of this. And with that, actually, I want to come to my last outlook. I hope I could convince you diamonds are a quantum network's best friend due to all of their great properties. And with that, I actually want to conclude. Thank you for your attention. Thank in particular the two students which were actively working on the results I have presented to you today. Thank the full team and all of our collaborators. And with that, I want to ask you for questions.
Thank you, Katharina, for the wonderful presentation. We have some questions for the public. The first one is for Brandon. What first drew to you study quantum networks and diamonds as a qubit platforms?
Can you repeat the question?
Yeah, sure. What first drew just to study quantum networks and diamonds as qubit platforms?
It's actually a very great question. The qubit platform actually of diamonds was heavily explored in Ulm already. So in Ulm, my professor, Professor Feder is one of the pioneers who was actually using one of the color centers, which is not a Group 4 color center, but a different color center called the NV center for sensing purposes. But they found actually that so the NV center is a great qubit system, which allows you actually to do some of this qubit control at room temperature and so on. And it was shown that it can have very long coherence time. It could be quite scalable. We can have actually all of the necessary ingredients of what we need for a quantum network node, but it was a little bit lacking of the efficient line matter interface. And this actually started to bring us to some other family of color centers, which was then the Group 4 color center family.
Wonderful. So the next question is, how do you see diamond-based in quantum networks impacting communication technologies in the next decade, in the next 10 years?
Also, a very nice question. I like these questions. They are very engaging and fruitful. Communication technologies is that's a very good thing to bring up with the communication, and in particular with the Group 4 color centers. And that's what I tried to show here. One of the last slides. It's already brought to telecom wavelengths. However, so what is a little bit a a problem still is actually that we have a very different platform. So I have shown to you that we have a full family of color centers. And so here one of the next challenges is actually that we bring all of these color centers to the same telecom wavelength, because you maybe may remember that all of them are actually emitting in some different ranges. But if we do so, actually, we can think really that we're pushing the boundaries of quantum communications, not only because of the platform itself, but it was also shown that these group 4 color centers are compatible with other platforms. For example, when we are talking really about some entanglement rates, the entanglement rates of the group 4 color centers are not the highest ones. One of the highest ones are actually arising from the quantum dots. There really it can be in the kilohertz regime. But it was shown that actually we can interface the quantum dots and harnessing their high rate of photon generation, and combine it actually with the memory times of the group 4 color centers. So there's a lot of work to do, but if you're really kind of like going for an hybrid approach, I really think that we can push the boundaries and definitely demonstrate there some key distributions, of course, but hopefully also kind of like building really a cluster of so really a network which can allow us to do this blind quantum computing on some yeah larger scale, maybe not already commercially available, but already kind of like available, such that quantum algorithms can be computed over this kind of like over this network, so on a larger scale.
Thank you for the answer. We had another question. How do diamonds color centers compare to other solid-state qubits in terms of scalarity and coherence?
Oh, this is also a very, very good question. And I hope, ha, wonderful. So I tried here actually this is actually from a review paper which was coming out 2023. So it's not completely updated. And actually the results I've shown you today are still missing in this table. But there's several things we need to consider, and one of them is about quantum memory time, quantum register, and the emitting properties. And if we compare, for example, now like the D2 times, we can see, okay, atomic ensembles with 16 seconds are the super leading ones, but with the 20 milliseconds comparing to the rest, for the electron spin, we are quite well suited and quite competitive in this field. When we are talking about the quantum register size, we can see that for the quantum, the single atoms or trapped ions, this was already 4. And for the NV center, it was already 9. So there's actually a quite big number already. So we are a little bit behind with our 3 identified, but 2 already controlled additional qubit systems. But with our 2 seconds, we are actually also very well within some good regime. Of course, we need to perform better. We have to push it longer, but we have simulated it is possible. There are some little tweaks necessary. When we are looking on the emitting properties, and this is actually one of the properties which is very important, then of course we can actually see that looking on the Debye-Wallach factor, so again, like how many coherence photons I have, we are very well located actually with our 60% within the whole table here. And for the atom or atom photon entanglement, so electron spin and photon entanglement, I have shown you that we have a single shot readout of 95%. So we are also actually here in the higher regime in the fidelities. And so I think kind of like group 4 color centers are very competitive indeed to the other systems. But I still think that a hybrid approach would bring us faster to some working quantum network.
Okay, thank you for the answer. We had another question. Can you explain in simple terms how the photons for diamond defects can be used to connect distant quantum memories?
Um, yes. In particular, let's try to do it with this picture here, or maybe even go back to the beginning where I tried to introduce it. It was quite fast. So um, what we actually need is that we or what actually want to have is that we have here some two quantum memories which are some distance apart, some length L0. So, and what we want to have is actually that in the end, memory node 1 and memory node 2 are actually entangled with each other. So, what does this mean? So, to have this entanglement, we need to follow the steps of kind of like transporting kind of like the entanglement over this distance. And this is actually done by using the flying qubit, the photon, which is already entangled with the quantum memory. So I have a photon which state is depending on what I do have in my quantum memory. So probably you heard already a lot about belt state. So like if my quantum memory is enough, like I do have a photon or a bright photon. If I have a memory and down, I don't have a photon. And by kind of like now sending these photons, which I have or don't have, and sending them onto a beam splitter and performing the belt state measurement. So I actually sending, I'm actually extending the distance already between this part here of the quantum memory and the photon. So there the entanglement distance is already increasing, increasing, increasing. And by now hitting some beam splitter, which is really distant, we can and interfere these two photons with each other. We can swap the entanglement and so kind of like have the distance which the photons could travel. I hope this goes the right direction. Unless else, please put other questions. I will try to answer them.
Yeah, we had another question from Diana. What advice would you give you to young researchers interested in joining experimental quantum technology projects?
I think my best advice is to be open. There are great achievements on all platforms. There are already companies really focusing on certain platforms. We have seen that big focus is actually on the superconducting qubits. But what I try to emphasize here is actually, even though when we're pushing the limits there, we still need to kind of like scale up on kind of like on a global uh, distance. And this is just not so easy with these superconducting qubits platform because they're actually it is possible by but just few meters and not kilometers or even hundreds of kilometers. So one would need some interface to the photons, which is actually allowing to push the boundaries. And here, I think there are so many different formats, and it is important to keep the eyes open, to be open which platform can work, and also which platform combination could work. Actually, there are currently also some researchers going on which are trying actually to connect the group 4 color centers capabilities with the photons and the spin state, called like this efficient Lie matter interface, to interface this with superconducting qubits. So actually now what we would have in terms of Google, IBMs, or the others, kind of like quantum computers, when we just put kind of like group 4 color centers aside, we can use the capabilities and connect their big quantum computers with each other. And maybe the second advice I would give is just to start somewhere. I think it does not really matter where exactly you're starting at. Just be open. Try to understand a platform. Try to think in a bigger picture, and yeah, be creative.
Thank you. for the answer. Another question is, how has the collaboration across international labs advanced in the development on solid-state quantum networks?
So I think the collaboration is a very important thing. So we would not have us come so far when we wouldn't have our collaborators. So there's a lot of things which we need to think about, which is like starting from the fabrication of this defects over to kind of like coherently controlling it, tackling there the challenges, interchange about the challenges and also about the solutions, also interchange about um, the possibilities. And I think a point where now the collaborations are also a little bit moving into a different direction is that not you as a collaborator are not only responsible for a single part within the quantum network node, but you're kind of like a part of a quantum network. So now, at least in Germany, we're building up a quantum ecosystem. We have quite few projects which are actually trying to really connect the different quantum nodes, which are, for example, in Munich, in Berlin, in uh, Karlsruhe, in Stuttgart, to interface them with each other to overcome real distances. And this wouldn't be possible if there wouldn't be some collaboration.
Um, we still have two more questions. How do you balance the fundamental research with application that could be deployed in real-world quantum networks?
I'm very sorry. I think my internet connection was unstable. Can you repeat the question?
Yeah, sure. How do you balance the fundamental research with application that could be deployed in real-world quantum networks?
So I think there are a lot of possibilities and how to push it there and how to also increase the understanding and also push there the research. And so it is all actually coming down to have a more and more scalable system. So to kind of like having the capabilities and to control more and more of the qubits together. And also then, in the sense, sharing the entanglement over these distances, sharing the entanglement also within a small qubit register, this can all push the boundaries.
The other question is, what was the most surprising result that you encountered whereas you experimenting with group for colon centers?
The most surprising, it's a good question. It's actually uh, um, it's all about the details. So it's very funny. So actually, there was already a lot of progress going on with the Envy Center. So the Envy Center, like another solid state spin, another color center in Diamond. There was a lot of things already explored. It's already known for quite some years. There were great achievements done. They could already address, I think, actually up to 50 qubits they could identify, and I think up to 10 they could address. And but there was a little tiny detail that the Envy Center has a spin one system and the Group 4 caller center has a spin one half system. And at the beginning, I would not have even kind of like thought about what difference this can make, what additional challenges this can actually bring. So just to maybe also again connect a little bit to my talk, what I've shown you. So for Envy Center, there's no part which is missing here. It's much more sensitive to the C13 part, like C13 spins. However, it's again about looking on a great picture. So the Envy Center has its strengths, but when it comes to a quantum network, it lacks definitely the efficient spin photon interface. And this is all these details are actually coming together and yeah, but that kind of like only a change from a spin one to a spin one half nature makes a big difference in the addressing. That's something which was a little bit surprising for me, yes.
Thank you, Katharina, for the beautiful presentation. Thank you for the invitation, also to share your knowledge for our event.